stabilizer is the poly Z operator. So the stabilizer group is a group generated by all the stabilizers. So in the case of ket 0, the identity obviously stabilizes anything, and then you have Z. For ket 1, it's stabilized by minus Z. So the group is I minus Z. So the stabilizer group is always going to be an abelian group, where every element squares to the identity. Ket minus is stabilized by minus X. So I minus X. Here's a bell pair 0, 0 plus 1, 1. So this guy, it's stabilized by ZZ and XX. So ZZ because these both terms have even parity. XX because, well, if you flip it, if 0, 0 becomes 1, 1 and 1, 1 becomes 0, 0. So the stabilizer group is I, maybe you could write II on 2-qubit identity. IZZ, XX, and then their product, which I guess is minus YY. And so these are the generators of the group, and this is a full group that includes all products. And so the generators are not unique. So for example, this state here, it's generated by ZZ and XX, but it could also be generated by ZZ, oops, and minus YY. That was the impression.
What? No, ZZ and XX are tensor products?
Yeah.
Okay, cool.
Always tensor products
Gotta
implying.
get used to that still.
Yeah. That makes no sense. Yeah, so in this example, Z tensor Z and X tensor X are one set of generators. Z tensor Z and minus Y tensor Y is another set of generators, or we could have XX and minus YY.
So writing II is like not even that silly, honestly.
No, it really isn't.
Yeah.
So minus YY is also the stabilizer.
I mean, sometimes I instead of writing I start writing like
no.
one to mean the identity. Yeah.
Is minus YY also the stabilizer for the state?
It is. Yeah, I mean, you could check that if you wanted, but it must be because it's equal to XX times ZZ. I mean, it's true because.
No, you didn't put it there in the list of stabilizers. That's why.
Right. Well, so these, So what I'm writing here is these are actually not the stabilizers. These are a generator, a minimal set of generators that generate the group. So K equals N independent operators. So I didn't write minus YY because then they wouldn't be independent. The third one would be dependent on the first two. But you can take any two of the three. Okay, here, 0, 0, 0 plus 1, 1, 1. What are the stabilizers, or what's a set of stabilizers? CZZ? No. We don't. Alright, so it's nice. We don't need to mix Z's and X's. So either it's Z's and I's or it's X's and I's. We don't need to worry about mixing them in this example.
HHH.
No. No, you're only allowed to use poly operators.
Okay.
I mean, if you just use all X's and switch them all.
Yeah, XXX works because XXX takes 0, 0, 0 to 1, 1, 1 and vice versa. Okay, so that's a good one.
Can we do like a negative I, Y, Y, Y?
No, I don't. Well, maybe you could, but I don't want to do that. I'll just do Z's.
Negative Z?
No, because this is even parity and that has odd parity.
Oh, yeah.
IZC.
Yeah, because the second two have even parity in both terms.
Then we should have ZIZ, such a thing, ZIZ.
Sorry, you need
Z,
to revision.
I, Z.
Yeah, or ZZI or ZIZ, whatever. Yes, so basically you can take the parity of any two of the qubits and it's even, so that works. And so that gives 3 stabilizer generators. The stabilizer group in this case is going to have size 8. So I don't know. So you get ZZI, IZZ, ZIZ. And you get all this times XXX. Okay, which I don't know what that is. Minus YYX, minus XYY, minus Y Yeah, so that's eight operators. Again, you can choose not any three, but almost any three over here to come up with different generators. But so this kind of state here, where the stabilizer is split into terms that only involve x's and i's and terms that only involve z's and i's. These are called CSS states. I'll talk more about this later. Like one thing to notice here is that if you think of these as binary strings, so this is like 1 1 1, this is 0 1 1 1 1 0. This matrix is dual to this matrix.
Which matrix?
So
So the matrix of the x stabilizers, where every x is turned into 1 and every I is turned into a 0, and the matrix of the z stabilizers, where you do the same thing. Those matrices the rows of them are orthogonal.
Okay.
Why? Because the x's have to commute with the z's. So every x operator has to have an even overlap with each of the z operators, so that they commute. I mean, automatically the z's commute with themselves and the x's commute with themselves. So the only question is, do the x's commute with the z's? So that's So one way of solving this question would be to observe first find the x stabilizer, then you just take the dual of this of the 1 1 1 string, and that gives you the z's. Yeah.
So what's the relationship with the Gauss-Lagrange theorem? So you mean the dual?
I'm not there yet. I mean, so Gauss-Lagrange is for applying unitaries for simulating stuff. So far, we're just talking about states. But I'll talk about unitaries as well. I just want to keep on going through some more examples. Okay. Here, I'll do 2 more examples. But maybe the second one's too complicated. But let's see. So here's let's do this example. What are the stabilizers? Or what is a set of stabilizers? Stabilizer generators?
Okay, this one you can do negative ZZ, right?
Yeah, because they both have odd parity.
Yeah.
So minus ZZ is a fine generator. Minus XX, yeah. Alright, so the stabilizer group is the identity minus ZZ minus XX, I guess minus YY.
Yeah.
Okay. Cool. Here, let's do one more. Okay, so let's do plus YY.
Or maybe this.
Well, I figured that this minus sign cancels that minus sign.
Oh yeah.
So ZX is like, I don't know if it's plus or minus I, it's Y, but it's 1. So you get two of those I's.
Two I's,
Minus
yeah.
one. Alright, so here's one last example. Let's do, oh, this is going to be too complicated. Okay, I'll do a couple more examples. Let's do 0 0 0 0 plus 0 0 1 1 plus, no, this is 2. See. Alright, this
So
is
that
again.
one's 4Z.
Alright, 0 0 0 0 0 0 0
Okay.
plus 0 0 0. I mean, you can kind of guess what the answer's going to be because of the way I'm coming up with the questions.
It's an odd number of states. Something in mind.
No, I'm confused. Oh, I see. Okay. 1 0 1 0 1 0 1 plus 1 0 1. 0 1 1 0 1 0 plus 1 1 0 0 1 1 0 plus 1 1 0 1 1 0, 0, 1. Okay, so here's a state, and observe that it has 8 terms. So I should probably normalize it by square root of 8. But also that's a good sign because, I mean, it's good to have an even number of terms because, like, there's no way I could have 3 terms here and still have a stabilizer state because the x would have to pair up 2 of them at a time and you'd have one left over. So it wouldn't work. So the same thing's here. I got stuck because I had only written down 6 terms and that wouldn't make any sense because that's not a power of 2. So things, yeah, it would have been a problem. But I think this works. Let's see. You want to see any stabilizer?
All z's between negative.
It's 4, so all Z is fine.
I think you're right. Yeah, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2. Yeah, it's all. Yeah, good. So Z tensor 7. How about for the x's? I think the x's are actually easier.
No.
Really?
Yeah.
I would have expected another state with all the ones.
No, it's not. Yeah. Yeah. Well, so notice between here and here. I mean, the way I wrote this down. If you compare the first column to the second column, what's the difference?
Z, X.
Well, just I, X, X, X. Or, I mean, it could be that, but it's also just I think. I guess you're right. So another stabilizer is just Z, 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 I. The first 3 always has even parity. Right, so that also works. Right, but that's not what I was looking for. Here I was looking for the I, X, 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 X. It swaps the first column with the second column. So that's a stabilizer. Okay, so then do the same thing if you like for, I don't know, the first half of the second half. You see what that does?
Shouldn't we take Z, X, 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 X?
That's a.
Yeah, I mean, okay. Yeah, I mean, well, both of them. Z, I works, but so does I, X, 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 X. And so you could take the product, but we don't have to. Yeah.